Happy afternoon. Got blue skies here in the Hayward Hills. It's pretty nice. That's good news. And we're going to cover the second half of Chapter 5. And that's where we left off. And now we're going to expand our definition of present value because before we looked at the present value of one future sum or one future value. We used, I believe it was, let me pull up the equation here. Right, we looked at this equation, and it was for a future value at a single point in time. And so what we're going to do today is we're going to expand this. So instead of looking at just one FV, one future value in time, we're going to look at how we can calculate present value of lots of FVs. So we might have a cash flow or amount of money in year 1, in year 2, in year 3, and how do we take the present value of all those together at the same time. So we're going to look at a couple different cases of that. And so we're taking the present value, and so this is the first cash flow at time 1. You can think of this as a future value at time 1. And so we're going to take that, we're going to discount it back to present value by 1 period. So that's what the 1 stands for, right? And so then the cash flow at time 2, we're going to just directly add that, and that's being discounted back 2 periods because it's at time 2, right? And we could just go on and on like this for as many periods we have in the future with cash flows. So let's go ahead and try a question here. Find the combined present value of getting $1,000 in 1 year and $1,500 in 2 years if R, the interest rate, is 10%. What I find the easiest way on some of these problems, at least for me, is to visualize when all the different cash flows happen, because sometimes these problems can get a little more complicated as we go on, and we have 3, 4, 5 different cash flows, and we have to figure out what the total cash flow is in every year. And so a tool to do this is the timeline. And here's an example for this problem. So the timeline goes from year 0, 1, 2, and 3, and then you'll see how under year 1 we have the $1,000, and under year 2 we have the $1,500. And so what this process is doing is basically discounting the $1,000 back to time 0 and discounting the $1,500 back to time 0 as well. The $1,000 gets discounted back 1 period, and the $1,500 gets discounted back 2 periods, right? And so you can kind of visualize all the cash flows have to be brought back to time 0, and since they are, then we can add them up because they're all caches, they're all values that are at time 0, so they can all be added up, and then we can find the single value for a whole stream of cash flows. And then when we're comparing examples, we can directly compare one option versus another option because they're all a single value at time 0. So we're going to go ahead and discount back each period. Here's the first cash flow, $1,000, and it's discounted back 1 period with R equal to 10%. And the second cash flow of $1,500 is discounted back 2 periods. And that gives us a final value of $2,148. So that's the present value of these 2 cash flows. There's another way we can do this using an Excel function. It's called the NPV function. Now we're going to be covering NPV, or net present value, as a tool in finance in a couple chapters, but I'm introducing the Excel formula for it now because it makes solving these problems fairly simple. What we need to do this, same example we just covered, but using the MPV formula is we need R, the rate, and then we need to know the different future values or cash flows at each time period. So in this example, this is the same example we just covered, same timeline of cash flows. This is what we would input into the NPV Excel formula. It would be equals NPV, the interest rate of 10%, the cash flow time 1, and then the cash flow at time 2. And if you do that, you'll get the exact same answer as we did before using the math. Let's look at another example. This time the interest rate is 8%. That's the amount money costs us. And we have two options. The first one is we could buy this car for $15,500 now. So let's put that in present value form, because again, that is the key technique that we use when we're analyzing financial options. Always take it back to present value. What's the present value of 15.5 right now? That's just 15.5, right? So it's already in present value terms because it's now. Let's assume that the other option is to pay $8,000 now and then $4,000 at the end of each of the next 2 years. If we put that on a timeline just to organize it, it's going to look something like that. So now let's go ahead and take the present value of it. Now check this out. This is a little different than the last example. The $8,000 right here, you notice how we're not dividing it by 1 plus R? And that's because it's already at time 0. So we just leave that be by itself. So if we have a cash flow at time 0 and we're calculating PVs, present values, we don't have to do anything to it. So I left that by itself. But then the 4,000, that has to be discounted back 1 period. And the 4,000 at time 2, that also has to be discounted back, but 2 periods. So this should give us the answer for option 2, which is going to be 15,133. Okay, so now what we do is we compare the different options and we compare those present values and we choose the better one. And since this is a cost, we're comparing the cost of 2 different options, we should choose the lower one. And we would choose option 2 since it's 15,133 as opposed to 15,500. There's another way to do this problem, and that is using the Excel formula for MPV. So this is what it looks like. And notice how the 8,000, I left it outside of the MPV formula. And that's because, again, it's already at present value times 0 terms. So we don't have to put it into the MPV formula. So the answer to do this in Excel is 8,000 plus NPV 0.08, 4,000, 4,000. Okay, and if you do that in Excel, you'll get the same answer, 15,133. So choose the lower option. Okay, so that was the Excel version right there. Now let's look at a particular type of multiple cash flows. This is called a perpetuity, and it comes from a set of cash flows that's perpetual, meaning that it will last forever, as far as we can tell, right? But at least that's the assumption. And it comes from the idea that sometimes we set up entities. It could be a trust fund, it could be an endowment, and the intention when those funds are initially set up is that they will provide a stream of cash supporting some type of endeavor forever. Here's the formula to calculate the present value of a perpetuity. In this formula, the C is the cash flow that we want to happen every single year going into infinity. R is the discount rate or the interest rate per period, and then P is the present value of the perpetuity in this example. It's a pretty simple setup, right? Just figure out how much you want the perpetuity will pay for every year, for example, and divide it by the interest rate, and that's the present value of something that goes on to infinity. Let's do an example. Suppose we wanted to create an endowment for a new charity, which will pay the charity $100,000 per year forever. So that's the idea behind endowments, and a lot of nonprofit type investments are set up like this. This is an endowment for a charity. Another example, universities, when they set up scholarships for students, very often if like an alum or something like that is donating money for a scholarship, they will do the calculations on how much has to be donated to support a certain amount of dollars scholarship per year using this formula. So this is what, so like in the question here is, if you want this endowment to give off $100,000 per year forever, how much do you have to invest today, assuming an interest rate of 10%? How much do you have to donate today into this endowment so the charity can receive $100,000 per year off this endowment? So this is an example of the perpetuity formula. There's the timeline. Payments go on forever. And here's the formula we use. It's just C, which is the cash flow, 100,000, divided by the interest rate, which is 0.1. We do the math there, and we get $1 million. So think about this. If you can get a 10% interest rate, let's assuming you can guarantee that forever. That's a debatable one. But if you put $1 million into an account and it gets 10% interest, that's $100,000, right? So every year, that interest is going to be taken off and given to the charity in this case. So it kind of makes sense. You start off with $1 million and you never touch that million, but every year you take that 10% interest and you give it away to this endowment. And so it kind of works, right? In the university scholarship example, the university typically uses 4% as the R for setting up an endowment. So if I wanted to set up a college scholarship, let's say the scholarship would pay $100,000 for a certain number of students every year. And the university is going to say, okay, if you want to give away $100,000 in scholarships to students every year, and you want to set up this trust fund to do this, we're going to divide that by 0.04, 4%. This is how the university does it, not this example. But the university is going to use 0.04%, and then they're going to say, okay, how much, then they're going to tell the person how much they have to put into the trust fund to be able to do this. So let's go ahead and calculate this right now. Let's see who can come up with an answer first. It's going to take me a little while. I'm going to draw it out. So if we let R equal to 0.04, what's PV going to be? Does anybody have an answer on that?
2,500,000.
So that's what you guys are going to have to do after you graduate. If you want to so $100,000 in scholarships are given away by the university every year, you're going to have to put away was it 2.5 million?
Yeah, I got 2.5 million.
2.5 million.
So they would need to put like 2.5 million into an account that gives 4% interest.
Yeah, the university uses 4% because you know, this is something you have to assume it's going to last forever, right? And so you can't always assume you're going to get the stock market return of like 7 or 8% every year. Long-term bonds typically are in the 3 to 4% range. So that's what it's kind of a conservative number. Right now, long-term bonds might be a little lower, but you kind of have to take a longer historical view. And so it is possible if interest rates stay really low, that number would come down over time. And in the future, when you guys are ready to give your 2.5 million, they're going to say, you know what? It's not 4% anymore. Maybe it's only 3%, and now it's going to take, you know, 3 or 4 million to do the same fund that gives off 100,000 a year. So what you said that was two. That's yeah, 2.5 million. I think I shouldn't be doing this.
Yeah, it's really hard with that Zoom whiteboard pen. I don't like it.
Yeah, my 4-year-old's doing this for me right now, actually. Yeah.
Wait, why are you dividing it by 0.04? I'm sorry, I'm confused where you got that from.
So I asked an example, what would happen if R is equal to 0.04 instead of 0.1?
Okay, that makes sense.
And so what happens as the interest rate goes down, we're going to have to put more and more money into this trust fund so that the charity or whatever it is can still get the same amount of cash flows every year. As that R goes down, the PV is going to go up. That's what it says. We have to put more and more money into the fund to get the same amount coming off of it every year because the interest rate. Let's talk about an annuity. And the annuity is basically like a perpetuity, but it has a defined life. It does not last forever. Here's the equation for an annuity. It's a little more complicated. As you can see, where this comes from mathematically is it basically takes the value of a perpetuity and then subtracts from it the cash flows that happen after the annuity. I don't think it's really beneficial to us to go into too much into the details of the derivation, but it's a little kludgy in terms of having to do it on paper and calculator, but it's quite doable. We will also look at how to do it in Excel. Okay. Somebody asked a question. I don't know what the heck it means, and I'm afraid to ask if this is some kind of. It looks like someone's trying to Zoom spam us or something. Hey Timothy, was there? I have no idea what you mean by that question in the chat. Can you rephrase that question?
Oh, the Trinity study, like it was like something I heard about. Like sometimes when people retire, they try to take out 4% or something because they say like there's a certain percentage like likelihood of if you do that for like 30 years, like you won't run out of money.
Oh, okay, yeah. So that's kind of like over the long term, you can pretty much be sure you're going to get 4% per year. That's what it says. Yeah. So yeah, that must be what it's, that 4%. So it's a pretty common number to use. I wouldn't be surprised if over in the long term, you know, with interest rates being low, that people don't start dropping that to maybe 3.5% or something. Let's do an example here. You purchase a TV by paying $1,000 per year at the end of the next 3 years. What is the price you are paying if the interest rate is 10%? And what I mean by what is the price you're paying, what is the present value? What is the real price you're paying for that TV today, given you're offered this payment plan of $1,000 per year every year for 3 years? This is what the cash flows look like on a timeline. And so our goal is to get all these 3 cash flows back to time 0. and find the total sum of those cash flows. So this is how we would do it using the math. We take here's the cash flow, the C, right? And then the equation from the other slide, the next is 1 over R. And then you have 1 over R, this term, R times 1 plus R to the power of T. And that's just the total number of years in this annuity, which is a 3-year annuity.
Wait, which slide are you talking about?
This 26, the one I'm on right now. So what I'm saying is this equation right here, right? That's the annuity formula that we covered on the last slide.
Right. What's that 1 over 0.1 is? The first one is from the formula, right?
That's this 1 over R. You know, when you type things out in text, it's hard to make it look like a pretty equation sometimes. So this is that first term right here. And this is the second term within the parentheses, right?
Yeah, right.
Okay. And then if I go to the next slide, here's that first term, 1 over R, right? And here's that second term within the parentheses. So this is that same formula as you saw on the previous slide. It's just written out in text form with the numbers and everything. And so the answer we end up getting is 2490. Okay. Were there any questions about how that was calculated?
I did the calculation on my calculator and I got 2486. Is that like close enough?
It's close enough for government work. I'm sorry, that was a bad joke. Let me see here. It is possible that here's the thing on these types of problems, rounding can play a big role in the answer that you get. So on some of these annuity problems, I'll try to make sure that there's no answer for none of the above, because then that could mess you up if you're off a decimal or two, right? So I will just make it so it's close enough that you choose the closest answer. But you can be off a little bit different, because if you're doing all these calculations by hand, you round a little, right? And so a small rounding can create a little difference in the answer for these. It is possible that 2490, maybe I didn't do any rounding when I calculated that. Did you do rounding when you calculated it?
I just put the first thing without doing the 7.51.
Okay, so maybe your answer is a little more exact than mine. That's possible, yeah. I think mine, I must have done some rounding. Okay.
Okay.
The next way to do it is using Excel, and we actually have. There are 2 ways you can do this in Excel. One is to use the NPV function, and that's pretty easy. You put in R right there, and then after R, you list the cash flows at time 1, then the cash flow at time 2, and then the cash flow at time 3. And so the equation just looks like this right here. And that should give you the same answer as what we had before. Another way, and this may not be as intuitive because it's a different way of using the PV Excel formula that we looked at on Monday. All right, and that formula, if you recall, is right here. And when we use that formula, right, the first thing you put in is R, the interest rate, and then you put in the number of periods, right? That's all pretty easy to understand. But when we were doing it on Monday, this part right here, payment, we set that to 0 every time we did an example with it, right? And all we did was worry about this other part here, the future cash flow or the future value. And we set this to 0 right here because that PMT is defined as a payment that happens every single period. Well, it just turns out, right, when we do annuities, that's perfectly exactly what we want. And so we can use this PV formula to solve annuities. And it has an advantage over using the NPV formula we did in Excel number 1 here, because imagine if we had an annuity that lasted for 40 years or 30 years. In the NPV formula, you would have to put out, 40 or 50 of these, and nobody would want to do that, right? So this makes it really simple using the PV formula. So we basically put in R, the interest rate, the number of periods, and this right here, that's the payment that happens every single period. Okay, and here's the tricky part. What that means is we don't have a single lump sum cash flow future value at the end. And that's why there's a 0 right here. All the cash flows are taken up because we plug them into the PMT, the payment right here. So if you do that, we should get that same answer as we would get using the MPV formula. I'm going to pull up my Excel. So in that first example, we did NPV 0.1. That's the interest rate you have to put in for Excel. And then you put in the cash flow at time 1, and then the cash flow at time 2, and then the cash flow at time 3. You notice here, when I write some of my numbers, I left out the commas, we would usually have between thousands. It's because if we do that in Excel, it's going to think that we're using a comma to show a separate year. So you kind of have to do it like that without commas in your numbers for Excel. So, and who was it? Somebody said they got 2487. And you're right, that is the right number. It should be 2487.
Do we have to use Excel, or can I just do it by hand or calculator?
You can do it by hand on the calculator. That's fine. Yeah.
Okay, I don't know. I feel like that works better for me. Excel I don't know. I just get scared about it.
That's no problem. This is a little different. I am putting a lot more Excel into our class this semester than when I taught it last time, which was a couple of years ago. And so, but I have it so you can do it in math as well, okay?
Okay, I'm just worried if the next quiz, are we gonna have to use it through Excel, or can I just punch it in the calculator?
You can punch it in the calculator.
Perfect. Thank you.
Yeah. And if we do it like this using the PV function, we should get the same answer. P1, 3 periods, $1,000 payment per period with no lump sum future value cash flow. And you see there we get the exact same number. Remember PV, FV, those functions, they do that weird thing with the negative sign. And so, but it's essentially the same answer. Oh, I will say, there are a couple problems that are very hard to do with the calculator. So if you want to do the math by hand, when you're figuring out the internal rate of return, you're going to have a hard time. And maybe we can talk about that at the end of class today. Here's another example. Let's say starting next year, you plan to save $4,000 every year for 20 years and then retire. Given a 10% interest rate, what will the value of your savings be at retirement?
So this kind of problem is the one where you'll have to use the PV, because for the MPV, you would have to write out 4,000 20 times, correct?
Yeah.
So
Yeah.
I see why the PV
And
one.
you can also do it by math if you want. But it's going to be a long, you'll see a lot of these problems can be handled multiple ways. One of the easiest things to remember is, just take the present value. That's kind of usually one of the first things you do, unless they're asking for like an interest rate or something like that. Now the tricky thing with this problem, let me pull up my annotation here. So look at this. So we're not putting away any money today, right? It's all about the future. So we're doing $4,000 per year for 20 years, right? That sounds like an annuity, right? So right off the bat, we know it's an annuity. And we've got R, so that's 10%. Okay. And so then you see here, we've got the annuity cash flows, and they're happening every year for 20 years, right? So if we take the present value of this, is that what the question is asking?
No, it's asking for the value of your savings at retirement.
Yeah. So it wants to know how much money you're going to have in the bank out here. This is what it wants to know, right?
That's future value, right?
Yeah, it wants to know the value of our account, the total value in the future at 20 years. Yeah, FV, future value. So how can we calculate that? What tools do we have to do this?
Do we have the future value equals present value times 1 plus R to the T power?
Yeah, we can do that. So we know present value.
So it'd be 4,000 times 1 plus 0.1 to the 20th, or no, to the 20th
Well,
power.
we know this, right? That we can calculate the future value if we have the present value, right? Right? But what's this? We need the total present value of this annuity. This is basically annuity right here. Is there some way we can take these cash flows and calculate the present value? We're going to use the annuity formula, right? So we can get the present value of the annuity by using that formula we just covered on the last couple slides. So we're going to use the annuity formula. Wow, this is dangerous. I apologize. So it turns out to solve this problem, it's kind of a two-step procedure. First, we take the present value of the annuity. That's step one right here. Okay. And then the second step, we calculate the future value of that present value annuity, and that will give us our answer over here in step 3. How much money do we have in 20 years? So it's not a simple problem because we had to use a couple steps to get to the final answer, but we've got all the tools to do that. All right, so that's the strategy of how we're going to solve this. Let's go and see. Let's go and see how the solution looks. So we're going to calculate the present value of the annuity, and then take the future value of that. So here's how we do it. Here's the present value of the annuity, and I'm just doing it in Excel right now, but you can do the same thing with math. Here's the present value of the annuity. Sorry. And we put in 10% interest rate, 20 periods, a $4,000 payment per period with no single lump sum payment at the end. And that gives us 34,054. So that means this stream of $4,000 being paid out or being invested over 20 years has a present value of 34,054. Now we take the future value of that using the same 10%, 20 periods, and now we put in the present value of 34,054, and it gives us a future value of 229,098. 229,098 is how much will be in our account in 20 years. If you want to see the math that does this, look at the notes on the bottom of the slide. The notes on the bottom of the slide are all about the math, okay? So please go ahead and check that out. Are there any questions about how this problem was solved?
No, I have a question about the calculator. My calculator doesn't show the interest rate. How do I find that?
I'm not sure what you mean.
I have
You have a financial calculator or a programmable calculator?
Yeah, it's a business calculator. It has N and I/Y. Is that interest?
Yeah.
Okay.
Yeah, I is interest. Hey, you know what? Why don't we talk a little bit at the end of class, and we can talk about how to use financial calculators, okay? So don't forget, we'll talk at the end of class today, all right? I'll try not to keep you too late. So it sounds like everybody got it. And if you did, I'm going to go on and I'm just going to show you a faster way we could have done this. I wanted to make sure you understood this way because given the tools that we have, this is how the problem is usually solved. We take the present value of the annuity, and then we take that annuity value at time 0 and we put it in the future at 20 years. That's how it's usually solved. But given Excel formulas, we do have a quicker way to do it. And that's right here. So bear with me for a little. This one's going to be a little, your mind's going to be blown away. So we're going to use the future value formula, and we're going to do it all in one step here. We're going to put in R, the number of periods. Now this time we're going to go ahead and put in the payments every period. And the payments for us is $4,000 every year. Now assuming there's no lump sum payment at the end, which we don't have because it's just $4,000 every period, this PV, when we plug it in, is going to be 0. So the formula, it looks like this. FV, R is 0.1, number of periods is 20, and the annuity payment every year is 4,000. There's no extra lump sum at the end, and boom, it gives us the same answer as before. So our traditional tools using time value of money math or using even some of the basic formulas we have in the calculator, they don't let us really do this. But in Excel, there's this easy way to do it. So you don't have to do it like this, but if you think about it, it does look a lot cleaner. And basically what it's doing is it's calculating the future value of an annuity. Usually we only do the PV, or present value of annuity, but given the formula, it does offer some flexibility to do that. Okay, so whatever method you prefer is fine with me. And I realize it does take some practice to get a hang of it, and we'll be able to do that. Here's another problem. Let's suppose we purchase a condominium for $200,000 with 100% financing. That means there's no down payment. So that means the loan is going to be for $200,000. The loan is going to be for 30 years and at 10% interest per year. If we make annual payments, I know that's different than most normal loans, but let's just assume annual for now. What will those annual payments be? So if you think about it, it's kind of like an annuity, right? The difference here is we don't know what those annual payments are, those cash flows every year. We've got a set of cash flows, they're all the same, and they're going to be 30 of them over 30 years. We know the interest rate. Do we know the present value of the loan? Actually, we do, right? That's the $200,000 purchase price. So if we borrowed $200,000 because we had 100% financing, that $200,000 is the PV. That's the present value. So we're going to use that annuity formula, plug in the PV, and then solve for the cash flow every period. That's the strategy on solving this problem. The other way to do it in Excel is going to be to use the payment function. Here's the numbers that we put in Excel. R is 10%. The number of periods is 30. The PV is 200,000. That's how much of a loan we get. And the FV is 0. So that bears some explanation. Why is the FV 0? Think about this as being our loan, right? And so initially the loan has a value of $200,000. That's how much we're given. But then over time, we pay down the loan every single year. Ultimately, the loan will be fully paid off and the value is 0 for the loan. So the future value of the loan is 0. You plug that in with the data and you end up getting $21,216. So that is the annual once-a-year payment for a $200,000 loan. And I'm just going to give you a quick show of the math here, because I know Iman wants to see the math. So let's look at the math. Am I right?
Thank you.
You're welcome. I hope I'm not embarrassing you. I'm not trying to. Okay. Are you able to see that? So here down in the notes, okay? So this is what the math setup looks like. The PV is equal to 200,000, and then we plug in C as our variable, and then we plug in all the information we have there for the annuity formula. Okay? And then we do the math, and we end up getting a little algebra, basically. And then we solve for C at the end, right? bear with my chalkboard here. Hopefully that makes sense. Okay. So you just have to do a little algebra to solve some of these problems with the math. Any questions on that that condo loan example?
Quick question. So for the
Yeah.
math part, so like I understand how to do it, but what throws me off, the first part, but the second part of the first part, it says, is it 1 divided by 0.1 times 1.1? Like where did you get the 1.1 from?
Are you
That
talking
part.
about down here in the denominator?
Yes.
Yeah, it's basically R times the quantity 1 plus R. And then you have to take that to the power of T. Bear with me for a second. I'm just going to go back to the formula up here. So it's basically this part right here.
Okay, that makes so much sense.
Yeah, I guess my typing out the formulas is causing a little confusion. Sorry about that.
Thank you so much. That helped.
So we're going to talk about a couple areas of interest rates, and including the difference between simple and compound interest, annual percentage rates, APR, which most of you probably see when you go to a bank or you look comparing offers on things, your bank account, what the interest is or what the loan payments are. We'll also look at something called effective annual interest rate, and then we'll discuss inflation. So what's simple interest? Simple interest is where you only earn interest on your principal, okay? And every year, when you do earn interest, you take it out so that the following year, you're still only earning interest on your principal. So you only earn interest on your original investment. That's the key. Give me an example here. If you invested $100 into an account and you got 16% simple interest, after 2 years, you'd only have $132. And what I mean by that is this is the interest you get from year 1, and this is the interest you get from year 2. Okay? That's simple interest. Now with compound interest, you always reinvest your interest such that the following year you get interest not only on your original principal, but also your interest from the previous year. So we reinvest our earned interest. And this is called compounding your returns because you're getting interest on top of interest. In this case, if we invested $100 at 16% compounded interest, we'd have a little bit more at the end of 2 years. We'd have 134.56. And the reason is this. So here's our interest from year 1, right? And this is our interest from year 2. And notice the difference right here. This is because at the end of year 1, we reinvested our interest and it went in to actually increase our investable base, if you will, in our account. So we're getting interest on our previous year's interest reinvested. That's the basic difference with compounding. And it seems like a relatively simple concept, reinvesting your earnings to get interest on top of your reinvested interest, but it is the key for saving for long term. And if you talk to a financial advisor, you take a personal finance class, they'll talk about how if you start early and invest your money over 20, 30 years, you know, it's like a hockey stick. It goes way up the value of your fund. And the key is reinvesting all your earnings. And without doing that, without the compounding, you can't grow your account like this. And this is only for 1 or 2 years, but it keeps getting bigger and bigger, the effect of compounding. So a lot of the interest rates you might deal with are not calculated on an annual basis, but they might be calculated on a daily basis or a monthly basis or some other basis. Like your savings account at your bank, I'm guessing that might be a daily interest rate that you get. And that's how they calculate it, based on how much money you have every single day. And your credit card, that might be calculated on a daily interest rate basis. Some of them also use continuous compounding, and that's a little beyond the scope of what we're going to talk about right now. But they're kind of continuously calculating all throughout the day your balance and how much interest you owe. But when interest rates are communicated to consumers, banks, credit cards have to translate their daily or monthly interest rates into an annual interest rate. And the way they do that is they calculate the APR, or annual percentage rate. And what that is basically is the periodic rate, which could be the rate they charge per day or per month, depending on how they calculate interest, multiplied by the number of periods in a year. That's the APR. And so if it was a daily rate, there are 365 days per year. If it was a monthly rate, there are 12 months per year. Right? So APR is used to communicate interest rate to consumers, but it's not the actual rate that calculates the interest you pay. The rate that does that is the periodic rate. Okay? They calculate interest per day, or they calculate interest per month. The effective annual interest rate takes compounding into account. And so that means it's higher than the annual percentage rate because it has this compounding. Why is this important? Because think about if you happen to have some credit card debt, right? And if, let's say, they're calculating interest daily, the effective annual interest rate will tell you how much your debt will grow over time. Because it's not based on the APR, it's not simple interest. Your credit card debt rolls over, right? If you don't pay your debt one day, the interest becomes part of your new principal that you owe for the credit card company. So there's a compounding effect to credit card debt. And so the effective annual interest rate will tell you how much your debt will grow over time, assuming that your interest gets put back into how much you owe to the credit card company. And that's calculated using this equation here. The EAR, effective annual interest, is 1 plus the periodic rate to the power of the number of periods per year, and then all of that minus 1. Let's do an example here. 2% monthly interest rate. Calculate the APR and the EAR for that. So the APR is the periodic rate multiplied by the number of periods per year. So it's just 0.02 multiplied by 12. So the APR of a 2% monthly interest rate is 24%. And again, that is what banks, loan companies, credit card companies will communicate with borrowers. Or if it's a savings account, that will be what they tell you what your savings account will pay. The EAR shows you how much your account will grow over time, as long as you reinvest your interest or you don't pay your accrued interest and allow it to go into your to make your loan bigger, like with a credit card. And that's calculated 1.02 to the power of 12, all minus 1, and you get 26.8%. Notice how it's a little bigger? Remember, that's from compounding because you're getting interest on top of your interest. What is the EAR for a car loan requiring quarterly payments at an 8% APR? So we have to find the equivalent, the EAR, and to find the EAR, we need the periodic interest rate. But we're not given the periodic interest rate. Instead, we're given the EAR. So that means to solve this problem, it's a two-step process. First, use the APR to calculate the periodic rate, and then two, use that periodic rate to calculate the EAR. Let's look at the steps here. So we got this formula for APR, and we can plug in the data that we have and use that to solve for the periodic rate. And so that means the periodic rate is going to be 0.02 or 2%. So on an 8% APR, where interest is charged quarterly 4 times a year, that means the periodic rate is 2% per quarter. Okay? Now we can use that to calculate the effective annual rate, the EAR. Here's our equation for the EAR. And now we plug in the information we have. So it's 1 plus the 0.02, all to the power of 4 periods per year because it's quarterly, and then minus 1, and so we get 8.2%. So it's just a little bit more than the APR, which is what we'd expect. Inflation is the rate at which prices increase. And we're usually worried about consumer prices because we're consumers, and that's tracked by the Consumer Price Index, the CPI, which is published by the government. I think perhaps one of the Federal Reserve banks does it.
Wait, I have another question.
Go ahead.
So the slide before this one about the ER equation, when you said the periodic rate is times 4, is it always going to be times 4? Because it's, only when it's quarterly.
Exactly.
Okay, never mind. I answered my question. Thank you.
What would it be if it was daily?
24? Like 20?
365.
Oh, daily. No,
Based on the number, it's always the number of periods per year. So if it's daily, 365 days per year, right?
365, got it.
Yeah. If it was monthly, it'd be 12, right?
Okay, that makes sense.
So we've got inflation rate. The next is nominal interest rates. So nominal interest rates are basically what we see around us every day. These are the numbers we use to live by. It's the returns we get are all nominal returns. When we talk about stock market, when we get charged interest rates for loans, those are all nominal interest rates. When the bank quotes us rates on our savings account, it's all nominal. So nominal is everything that we live in, okay? And I always find this funny, but real interest rates are not the real numbers that we live in. Because what real interest rates are really to tell us how much our purchasing power is changing with our returns or the interest we're paying. Okay, so just remember nominal interest rates, that's what we see every day. That's the world we live in, a nominal world. But real takes into account purchasing power. So let's look at it. Let's look at an example here, or talk about one. Let's suppose you put your money into a bank account and you earned 1% in your savings account. Okay? During that time period, let's say inflation was 2%. So that means during the time period, consumer prices, the things that you buy at the grocery store or wherever, increased by 2%, but your savings account only increased by 1%. So what real interest rates are telling us now is that we take into account inflation, and by putting your money into a 1% savings account, you're actually losing purchasing power because inflation was higher than the return you got on your money. And so that's why we use real interest rates, to help us figure out how we're doing in terms of our purchasing power. To calculate real interest rates, we have two different formulas. One is the real exact formula, and the other one is the approximation formula. The exact formula for real interest rate right here is basically 1 plus the nominal divided by 1 plus the inflation rate. The approximation formula is basically nominal interest rate minus inflation rate. The way to think about this is the approximation formula kind of takes into account simple interest. It's kind of like that. The exact formula kind of looks at compounding, and that's why it looks the way it does. Let's do an example calculating both. So using the exact formula, let's say we got a one-year government bond with an interest rate of 5.9%. We invested in that. During the year, however, the inflation rate was 3.3%. What is the real interest rate we got on that government bond? Okay, what was the increase in our purchasing power? We got a 5.9% return, but we didn't necessarily increase our purchasing power by 5.9%. The exact formula, like this, same equation as before, but sorry, it's written with text. Turns out like this, and that means the real interest rate is 2.51%. So we bought this government bond. We were pretty happy. We were getting a 5.9% return, but because inflation was so high over the year, our purchasing power only increased by 2.51%. That's what that's telling us. If we use the approximation formula, it's a lot easier calculation. It's just the nominal minus the inflation rate. We get 0.059 minus 0.033 for 2.6%. And so that looks, that's pretty close. It's the approximation formula.
For the test, would you want us to use the approximate or the real?
I would tell you which one to use. I think you'll see that in the homework too. That's what I did. The point is that if you're doing this for work and someone wanted you to take into account inflation, then you would do the exact formula. But if you're just talking to other people off the top of your head and everyone wants to know what's the effect of inflation going to be, then you would probably just use the approximation formula when you're talking with your friends. But for work purposes, you should use the exact formula. So nominal versus real dollars. For everything we do, we use nominal dollars, okay? And 100% of what I saw in my career was always nominal dollars. The only time we use real dollars is maybe when we're trying to communicate with people about the effects of inflation, to help them understand why maybe like investing in cash is not a good idea for the long term, putting all your savings in cash. That's one of the examples I've known where I may have seen it, but for work purposes, financial analysis, it's always nominal dollars. If for some reason you do have to use real dollars, just remember, if you're using real dollars, you have to use real interest rates. The two go together. And for our quizzes, everything we're going to do, where we're taking present values and things like that, we're going to use nominal dollars and nominal interest rates. And that is it for today. And I know somebody had a question about the financial calculator.
Well, we can do that now if
You got a few minutes now?
yeah.
if you go to our Blackboard site, under the materials for this week, you will see some slides on how to use a financial calculator. What kind of financial calculator do you have? Is it, are you using one of those bigger programmable ones where you can do like algebra and everything in them?
It's that one.
Okay, that's a regular one. Okay, yeah.
I
Right.
have a TI-84 plus CE, so that's why I'll probably be using. It's one of those
Oh.
programmable ones.
Okay, so the TI-84, you're gonna be on your own. I can't help you with that one too much. But they do have, it has the time value of money functions in there, and it comes up on your screen, and you just have to plug in the data for each of the like present value, future value, R, payment. So you should see that. But I don't have information on that. What
Yeah, I think I can find some information pretty well. I have some good experience with this calculator, so I can figure it out.
Okay. I'm going to pull up right now the standard, the business calculator that, is it Botter? I think
Yeah.
Botter, you were showing it, right?
Mm-hmm.
So here's the standard business calculator. And granted, this is a couple years old. I'm starting to move more toward Excel here. There are a couple things you have to make sure that are set in your calculator properly. You have to make sure it's in end mode. And the reason for that is the calculator can do the calculations assuming that the cash flows are in the beginning of the year or at the end of the year. And so everything we do, we have to assume is at the end of the year or end of the period. So
Yeah, I'm not sure how to put it in end mode.
right here. So you said an HP was at 12 or something, or
Yeah, it's actually the one on the right.
okay.
Yeah.
So here are the directions on how to do this.
Right, so I can begin.
So this is important just to set up your computer before you start doing the calculations. So just go ahead and follow all these steps right here.
This slide is in the course material.
Yeah, if you go to the week 5 folder, it's called Calculator Seminar. So that's the first thing you'll do. And then what the slides do, they go into a little bit more of the theory of how the calculators work and like why we plug in like positive numbers and we get back negative numbers. Remember in Excel? Well, it comes from calculators really. And then it goes through some examples here on how to calculate like future value and present value. It shows you what keys to hit.
Oh, that's perfect. Okay.
So why don't you do this? Why don't you go through this, do the setup, and start looking at a few of the slides, and then see what kind of questions you have, and we can talk again later. You can either email me to set up an office hour, or we can talk before or after class.
Okay, that works. Okay.
But you know, if you want to arrange another time, if that's not convenient, you know, we can see what works for both of us.
Okay, that's feasible too.